Thank you very much for this kind introduction. So this is ongoing work with Abhishek, with Manas, and Dipankar Roy. Actually, Dipankar is an example for this French-Indian sort of collaboration. I mean, he's currently postdoc in Nice. Okay, so I'm very grateful for this cooperation. I mean, it would have never been realized without sort of, having these possibilities. I'm grateful for being able to present my results here. So I realize it's a rather sort of diverse audience, and so I thought I'd spend the first 5 minutes explaining you just the standard KPZ, so you know what I'm talking about. And I will do this on the blackboard. I mean, for this purpose, I have to break the symmetry of this lecture hall. I could do it either here or here, no, so I decided to on this side. So, okay, so I will explain to you exactly the way how the experiment works. I mean, these are the famous Takeuchi experiments, and so let me just explain this very briefly. So, so here you have an interface, okay? And it's a two-dimensional film, and in the lower part here, I mean, you prepare the system in a stable state. So if you think of some free energy, I mean, sort of something like, well, something like this, and the system locally is sort of sitting in the minimum, okay? And so now you have some interface over here. Whereas in the upper part, I mean, you prepare something which is metastable. And so when I look at this situation, I mean, the system will sit in this metastable minimum. Okay, and then I just let it run. And of course, what's actually happening is that the stable phase is advancing and it nucleates at the interface. And, it keeps going. I mean, these nucleation events at the interface are quite easy to perform. And so, it's basically a constant rate. And so after a while, I mean, you will see that this interface has moved up. And of course, these nucleation events are random. I mean, so eventually you will see somewhere up here some random interface, right? Okay, so let me put some coordinates here. This is my height relative to the interface at time t equals 0, and this would be, let's say, my x-coordinate. And so you would describe this interface at some later time through some random height function. Okay? And what you measure experimentally is that when you look at these fluctuations, they're of order t to the 1/3. And if you measure sort of the lateral fluctuations, I mean, they're of order 2 to the t3. And that's usually called the 1 to 2 to 3 scaling, where, as you can see, this is h, I mean, this is x, and this is t. Now, the equation which governs this kind of experiment was written down much earlier. I mean, this is sort of around 2010, roughly, or 2011. And of course, it was sort of written down much earlier. That's this famous KPZ equation. And it's just an equation for this situation. I mean, so you look at the time derivative of your height function. So your height function, so it's it's time, and x is one-dimensional here. So there will be a nonlinearity which comes from the motion by mean curvature, which I don't go into, but I may just write it down. I mean, there's a parameter lambda, and then I have dx h squared. That's a nonlinearity. And then there's the stiffness of this interface, which is here normalized to 1/2. And then there will be noise. So this is the KPZ. Okay, and let me just make 2 comments on this KPZ equation. I mean, the first one is about this parameter. So the system is always critical, right? I mean, so no matter how I change the parameter lambda, I mean, you will always see the same scaling exponents. But what I want to say about this equation, I mean, you can put many parameters. I mean, you can put it over here. I mean, you can shift it by its rescaling space and time. This is the so-called dimensionless form. I mean, you somehow can reduce the large number of parameters to a single one, but where you put it is sort of a little bit arbitrary. I could have put it here or here, I mean, anyway. So that's just the conventional way to do it. And the other thing which I want to point out is that, whenever you do any measurements, I mean, like, let's say, fluctuations of the height, I mean, then you see that this parameter lambda just enters as a non-universal parameter. The scaling function which you measure in any one of these experiments is independent of the choice of lambda, except for setting, you know, a non-universal scale. So in that sense, I mean, we have a single universality class. Okay, so now what I want to do in the talk, and what is the whole project, is to generalize this situation, which is very, very well understood, to the case where H becomes vector valued, right? In fact, I will look simply at the case of two vectors. So in this picture, you can think that you have somehow two interfaces, right? Okay, so this is what I want to do. And let's see, the first thing, what I put up here is, okay, so you can, you know, just sort of naively put here, you know, the quadratic term, and then you put coefficients, and you have the components, and that's sort of the generic form. If you want to do the, let's say, n component, or in my case, n is equal to 2, if you want to do sort of look at this two-component KPZ generalization of the KPZ equation. Now, there's one important point, which is sort of that you see, I start here with the quadratic term. In principle, I should also put a linear term here. Now, if I put a linear term, what is happening is that the linear term dominates the whole motion. And when you look at these two interfaces, they will actually separate linearly in time. Okay, and if they separate linearly in time, you know, it's very far apart. And then you would think that essentially you could understand what's happening in the system by reducing it in a suitable way to this one-dimensional, to the one-component case. Okay, so this is not what I want to look at. I mean, this is something which, you know, also has been done, and there are lots of results. So my focus is the case where this is really zero, and this means that in this picture of interfaces, these interfaces are sitting on top of each other, and you know they strongly interact. And so now what's actually happening is a sort of much deeper riddle than when they are separating in time. Okay, now of course you can put all these coefficients here. But you see, I mean, just doing the mathematics like this, I mean, it's not so very so well directed. I mean, and fortunately, you know, I'm sort of in the situation that, you know, of course, we have seen actually such coupled equation already during this conference, but, you know, there are systems available in the literature, and so rather than trying to start to think about the general case, I look at the very specific case. So here is the evolution equation for one. I mean, you know, there has always sort of the same diffusion and noise term, but here's a coupling between H1 and H2, and here I just have the nonlinearities H squared and H2 squared. I don't think about any deeper reason. I mean, you know, we had to sort of reduce the number of parameters, and this sort of turned out to be a sort of a very nice choice. And again, it's sort of, you know, what I call the dimensionless form. I mean, you know, you have lots of parameters, but these are sort of, if you write the equation like this and you want to keep the form, then, you know, you need two parameters, but not more. Okay, and so the first person who looked at this was actually a polymer. I mean, so he was thinking sort of like a polymer, which is stretched in the x direction, and the H1 and H2 are the two components in plane direction. And then there's very nice work by Jacobo. I mean, he studied a totally different problem, namely the spin-spin correlation in the Heisenberg chain. But then he, derived effectively an equation exactly of this type, right? So that's a further motivation. And then recently there was even sort of even more direct motivation. I mean, this is sort of comes from this nonlinear optic, excitons and polaritons people, and they have sort of like two coupled, well, they have two coupled nonlinear Schrödinger equations or Gross-Pitagoric equations, so two condensates. And what happens in this case is that the condensates are, from physical reason, they are actually symmetric under interchange. And so you have to require that the equations up here for n equal to 2 are symmetric under interchange. And then, the system reduces enormously. You have still another non-universal parameter, which is capital T, but otherwise, it's exactly that system. Okay, so that's a good motivation. And so now the issue the question is, how does the universal behavior depend on these two control parameters? That's a simple question, right? And so here, for in this case, I mean, I have just one parameter, now I have two, and I have two components. The question is, what are the universality classes? Okay. All right, so let's see whether we can do any progress. So I should point out that there's one paper which it's published already, where we discussed quite at length, I mean, the case where these two coefficients are equal, and you will see that this sort of plays a special role. All right, so now let's see how we can do. Okay, so here I've written the equation. I mean, so now you might wonder about scaling exponents, things like this. Now you look at the literature, you sort of think about it yourself. Then you discover that if I just asking about the scaling exponent, nothing will change as respect to the one component case. You see, the point is that there's a separation of scales in these models, which just writing down the equation, maybe you cannot see. So the separation of scale means, this object is sort of acting on the microscopic level. It's just the noise and then the diffusion. But this is sort of acting on the masoscopic level. And so when you sort of exploit this kind of scale separation, then you realize that, that these two scaling exponents are exactly like what I explained to you here. I mean, it's a dynamical exponents we have, and this is what they call the wandering, I mean, the one half. So let me sort of state this sort of a little bit more clearly. I mean, there is a condition. I mean, the condition in order to use these heuristic arguments is that if I look at the steady state of this system, which of course I don't know, but I mean, let's look at it anyhow, or you can do simulations. The assumption is that you have a finite correlation length. So if I look at the steady state, so I here have written, maybe I didn't say this. I mean, you see here I've written things, maybe I should have explained this one. So here I've written the equation in terms of the slopes. I mean, the objects, the interfaces are moving, but the slopes are something which becomes stationary. So if I have a steady state which has finite correlation lengths, then you can do all these arguments, and you will find again sort of the scaling exponents as for the one component case. Okay. So here I've written down this static correlator. I mean, this is what I mean. And of course, now it becomes a matrix, and you can look at the dynamic correlator. So this also becomes a matrix. I mean, this is X and T. The average is always sort of in this steady state of these type of equations. And now you see that there's one sort of a big simplification is that when you look at this equation, then you see they are, sort of symmetric under the interchange. I mean, probabilistic symmetric under the interchange of phi 1 to minus phi. And therefore, this matrix actually must be diagonal, and also the dynamical correlator is diagonal. And so this, of course, is a big simplification because, eventually we just have to look at we have, I mean, for the dynamical correlator, it's just two functions. I mean, the two diagonal matrix elements of that correlator. And then, when I talked about scaling functions, so the exponents are fixed already, but now when I talk about scaling function is that when I look at such kind of dynamic correlator, it's not separately a function of x of t, but it scales, with this exponent t to the 2/3, so we'll have this form. I mean, this factor comes because, the integral over x has to be equal to 1, and so, that's just sort of the normalization, but, it just depends on x over t to the 2/3. And again, of course, it's not something like in the one component case where it can do a lot of computations, but anyway, I mean, you can sort of imagine that there is this scaling function. And now the issue is, how does this scaling function depend on x and y? You see, there are two possibilities which it can. It's just like in the one key case where the lambda just enters sort of as a scale factor. But it also could really change the scaling function. A priori, that's totally unclear. You see, for every x and y, I could have a different scaling function. If I would have, for every x and y, a different scaling function, this would I have many, many universality classes. They all have the same scaling exponent, but different scaling functions. Okay, so now we want to explore this. And now let's see, just 1 second. Yeah, okay, fine. Okay, and so rather than sort of letting you wait until the end, I mean, let me just show you what our current picture is, and maybe, it's still somewhat imprecise, but we will see, I mean, you will see what we know at the moment. I mean, so the picture, what we have is, first of all, so here I just plot the phase diagram. So here's x and y, And now the first observation, which I will explain in a second, is that when you are in the quadrant 2 and 1, 2, and 4, then actually the motion is unstable. This was somehow observed already by Kadar, but anyway, I mean, so it's unstable, so we don't even actually handle that case. Okay, so we are actually focusing on the case where it's stable, which is quadrant 1 and 3, and quadrant 3 is sort of not exactly the image, but sort of very similar to quadrant 1. So you can think that the action is really in this quadrant up here, okay? And now the claim is that there's a diagonal, the diagonal line is sort of a line of fixed points, and as I go along this diagonal, I mean, the scaling function will actually change. However, if I'm off diagonal, then it will flow towards diagonal in a very simple way, in the sense that it just, you know, keeps the same x values and the y value sort of changes, and then when I go to the actual scaling limit, it will sit exactly on the diagonal. So the claim is that the universality classes are now labeled by the parameter x, whereas the y parameter is, so to speak, an irrelevant parameter or sort of non-universal constant. Okay? Now, this is what we sort of found at the moment, and you know, now for the rest of the talk, I want to give you sort of, again, for each kind of claim, sort of a little bit of arguments of, you know, why this should be true. Okay. So now comes the first point about stability. I mean, this is something which is sort of very well known in the community of deterministic conservation laws. So I just want to make an example for an unstable system. So I just naively write down this equation, which sort of looks like two coupled conservation laws, but I put this minus sign here. And so if you differentiate again, I mean, you see that you get just the ordinary wave equation, but you know, the minus sign doesn't go away. And so I get the equation, you know, second derivative with respect to 2 is minus second derivative to x. I mean, that of course has exponentially increasing solutions, okay? And the general result is that if I take a hyperbolic system, so which I've written down here, right? I mean, so these are the various components. This is the current, which of course depends on the field. Then you push through. I mean, you know, we have seen this already in Jacobo's talk. I mean, you push this through. I mean, then you can write it sort of in this particular way, and then this is the flux Jacobian. And then the condition is that stability is sort of equivalent if this matrix, which, you know, doesn't have any particular symmetry in general, has real eigenvalues. Okay. Now, of course, you know, it's a slightly sort of touchy argument because it has to be for all phi and then you know, for all fields, and maybe for some fields it's true and not. Anyway, you know, there could be mixed situations which I don't want to touch at all. But for this particular case, you do, you know, very easily can check this matrix, and what you find is the condition for stability is that x and y should be, the product should be greater than 0. And so you see that I'm just basically in this and the reflected case, okay? So the belief that we should disregard 2 and 4, quadrant 2 and 4, just comes from this stability analysis. Okay, so now what is the next point? Let's see. Okay, so next time I always emphasize that, you know, we don't know so much about the steady states. I mean, that's certainly true, but there is sort of one general condition where we can compute the steady states. It's sort of the analog of what we know in one dimension, namely if these two matrices, the G1 and G2, which sort of give you the quadratic, the coefficients of the quadratic terms, if they are cyclic. I mean, cyclic simply means that they have this very particular form. In this case, that we still know that the stationary measure is Gaussian, and you know, the correlator of that Gaussian measure is sort of wide in space and delta correlate into the components. And so you know, you can sort of look at you know, cases where this is actually satisfied. And of course, the first obvious case is that, you know, if I take these coefficients equal to 1, 1, I mean, then it still looks like sort of interacting, but when you do rotation by 90 degrees, I mean, then you realize it just becomes two independent KPZs. So you see that, you know, the 0.11 is sort of, in a sense, the only one which we can easily solve exactly and completely reduces to the one component KPZ. Okay? Now we can do more. We can sort of do more analysis, and then you see that if you want to satisfy this condition, then actually it's not only valid at the point 1, 1, but it's valid along the diagonal. The entire diagonal is actually sort of true. And then we can do sort of numerical simulations, and we can sort of compute these two scaling functions. So, basically, we just have the two components, and each one of these scaling functions sort of looks like a Gaussian. I mean, so, roughly has this shape. But, as we go along this diagonal, I mean, we see that the G1 and G2 are not only changing height, but, it's also changing shape. I mean, so, I cannot, there's no simple linear scaling which would sort of, fit as I go along the diagonal. And so in that sense, what we see numerically is that, I mean, as I go along the diagonal, I mean, these two scaling functions really depend on the choice of x. Okay, and then you can look at, what is, for instance, the maximal peak, and you see this is the 0.11, and then this one becomes somewhat higher and the other one lower, and we did a lot of analysis of the case where sort of we actually go to infinity, which has some simplification, and then you see that the ratio of these heights is sort of 2. So I think there's very, very good confirmation that if you're going to go along the diagonal, then the scaling functions are not really connected to the KPZ function. Okay? So what we find here, numerically at least, as I go along the diagonal, I mean, we scan different universality classes. You see, it's always the same scaling exponent, but these scaling functions do change in a non-trivial way. Smoothly, I mean, it's nothing very spectacular, but they change in a non-trivial way with the parameter x. Okay, so now comes sort of, I think sort of, I mean, what I like is sort of the most beautiful part, because I didn't understand this for a long time. I mean, I read the paper Kadar, but now, somehow I picked up this paper by Funaki, sort of, which makes this very clear. And so let me just tell you the result. You see, the point is we have two components, and we can of course make linear combinations, right? I mean, make linear combinations, equation sort of looks totally different. Here, in this case, we don't make linear correlation. I mean, we don't want to do linear combinations anymore because we might lose that the matrix is diagonal. But in this case, I mean, for this particular case, I mean, it's still very useful. And so what you do is very simple. I mean, you take this R transformation and you rewrite your equations in terms of the new variables. It's just this linear combination. And what you find, lo and behold, is that you find two decoupled KPZ equations. Okay, so then you might first think, along the line x equal 1, I mean, everything decouples. I mean, that sounds a little bit implausible. Okay, and so you wonder what has happened. Well, what has happened is that the correlation between the two fields actually is hidden in the correlation of the noise. Okay, but otherwise it looks completely sort of what you think. And then you have this beautiful technology that rather looking at this thing, I mean, you make this exponential transformation. I mean, so you call this whatever partition function as e to the h. I mean, that sort of this simply defines what you mean by the Kohl-Hopf transformation. And then you rewrite the equation in terms of the c instead of the h. And now you get another equation, which is much studied, the stochastic heat equation. You see, it's like a Schrödinger equation, and it's linear. I mean, the C alpha appears linearly. However, you have to pay a big price, namely, now the noise acts as a potential, so it multiplies the C alpha. And the noise, of course, it's not like Anderson localization or so. I mean, this quantity, actually, it's noise in space-time. I mean, so here is a space-time noise. Okay. So now you might say, what can we do with it? But this is very well understood. I mean, of course, when you have this Schrödinger, the sort of Schrödinger equation, I mean, it's also generated by Brown motion. So you write down the path integral for this thing. I mean, so I just wrote down the action. I mean, so there's some factor how I put it. I mean, to get the x of t, but it's not so important. I mean, the main important is that you see you have this Brownian motion path. So there are two of them, one for component 1, the other for component 2, and now you have sort of a weight which is simply this integral. I mean, this integral integrated along the path, integrating this random potential. Okay, so this is the x coordinate and that's the s coordinate. This is space. This is sort of white, right? I mean, so. Okay, and this is sort of a model of what people call directed polymers. It's called directed polymers because, you know, these objects are moving directed in time, but otherwise it's really a polymer sitting in a random medium, right? I mean, so it's space-time is sort of dimension 2, okay? All right, but now you understand that, and now I have to tell you what is the noise, and you know, it's part of this computation that you find that the noise is sort of still delta correlated in space and time, but you know, there's this coefficient y here now, and which sort of makes it different from the independent case. I mean, you know, y equal 1. I mean, this would disappear, and then you really have two independent ones. Okay, now the question is why is sort of you know, why an irrelevant component? Well, you see, you think of these two directed polymers, and you have this delta x and you have the delta t. So you know, this deviation, I mean, this correlation act only when the polymer is actually, you know, when these two polymers overlap. But you know, you look at these polymers, and at least sort of heuristically, maybe one can even do a proof. You know, these events are rather seldom, right? I mean, they don't happen too often, and so they will be subdominant. And so, you know, in the long time limit, this will just converge to two independent KPZ equations. Okay. All right. So let's see. So I don't have so much more to say. So let's say what is the simple argument why we believe that you know, these flow lines are actually parallel to the y-axis. So this is a simple scaling argument, which I can sort of easily explain. So let's have a look. Okay, so now I'm imagine that you know, I look at this line here, and I want to compare xx, which is a fixed point, with, you know, another point xy, which is maybe sitting over here. Now, what you see from the simulation is that, as I said, you know, when I look for this particular parameter value, when I look at the correlator, it typically is extremely short-range correlated. I mean, but you know, it's not equal. I mean, here on this point, the correlator would be 1. I mean, here's some different value. I mean, so this integral, you know, it's maybe 0.9 or 1.2. I mean, it's just some different value, but it's not equal to 1. Okay, and so now let's do. You see, okay, so now the question is, you see, I have two parameters, and how do I even compare them? You see, I want to say that two models are in the same universality class. How do I compare them? And the main point is that, you see, I want to make sure that locally they have exactly, you know, the same sort of noise, the same invariant measure. I mean, you know, maybe it's a little bit coarse-grained because, you know, I mean, you know, I have short-range correlation, but once I do this little bit of coarse-graining, I should see exactly the same measure, right? I mean, so if I want to do it now here you see what I have to do in order to satisfy this. If I would compare two things which locally have different invariant measures, I mean, then of course, you know, coarse-grained invariant measures, I mean, then, you know, it's sort of, you know, comparing apple and pears. I mean, so this is a very important thing. Now here it's very easily achieved. I just have to rescale the phi alpha by 1 over square root of alpha, and then you see that the tilde now has variance 1. That's exactly how I can compare it. Yeah, I'm almost done, okay? So now I have plugged this into this equation, and I see that, you know, I get a simple rescaling of these coefficients. I mean, this can be absorbed. And now I have to look at these two coefficients. You know, this is still stays on x. So, you know, I haven't changed the x, actually. I moved somewhere else on this parameter. And now I make an important assumption, namely that when I look at the C1 coefficient, which is the correlate of the one component, at xy, I mean, you know, it should be different from the C2 component. Just saying that you know, what we observed in any experiment is that not both of them are 1, but, you know, one is 0.9, the other one is 1.1. I mean, this is an assumption which I make, and if I make this assumption, then you see I can satisfy my equation only. You know, I have a field which has now variance 1. That was this condition. Now there's this coefficient, you know, but the only coefficient under this assumption which I can put that this must be equal to x. Okay, and so you get, first of all, you get two predictions. First of all, you get the prediction that for some somewhat magic reasons, I mean, you know, these two susceptibilities must be sort of connected in this particular way. And the other one, you know, if I know that this condition is not satisfied for all points sort of along this diagonal, I mean, then the only solution is that this must be asymptotically equal to x. And so you see that the flow lines have to go parallel to the y-axis. Okay, so that's the end. I mean, so I just want to, I mean, just 1 minute to tell you, you know, what we see. I mean, so we have numerically, you know, I didn't put any sort of graphs because, you know, I mean, the graph itself, and I presume be less illuminating when I explain what we did. I mean, so here you have sort of the simulations along the diagonal. I mean, these are sort of 4 points. And then we have the Kohl-Hopf flow line. I mean, we have simulations which we did, and then there's the simulation of Weinberger. I mean, he started with flat initial condition. Anyway, so here we have a theory, and we have also numerical evidence. So this line, I think, is sort of undoubtable. I mean, this is certainly correct. And now, unfortunately, you know, away from that line, we have at the point x equal 2, we have only 2 points. I mean, if you look at the preliminary data, I think the overlap comes out reasonably. You know, this identity which I showed you is sort of satisfied, you know, maybe with a precision of something like 8% or so. Anyway, so, you know, it requires sort of maybe a little bit more work, I mean, and more simulations to actually sort of, you know, really fix this picture. But I mean, at least at the moment, I think it's a rather convincing theoretical argument. Thank you very much for listening.
Thank you. Questions?
Do I have what?
The tilt symmetry, you know, this Galilean boost.
Sorry, I mean...
The tilt symmetry. In the KPZ.
No, I just didn't understand the question. I mean, so...
No, so I'm saying in the single KPZ, you have this tilt symmetry, you know, this Galilean boost invariance.
Oh, you mean the
Do you have it also in the two component?
Yeah. Well, but it's not so useful. You see, the point is that when I'm in this two-component case, right? When you tilt the symmetry, then you actually get a net velocity for the you know, you get it. Okay. So if how should I say this? If in this two-component case, if you tilt the symmetry, then you know, you pick up a linear coefficient which you cannot remove by Galilean invariance. This is, I guess, what I want to say.
The chi plus z is equal to 2 is not a consequence of the symmetry anymore.
Yeah, that's the point. I mean, so then you see, here I insisted always that you know, the first term, I mean, the linear term should be 0. But if I start tilting the surface, I mean, then, you know, just do the simple computation. I mean, there's a quadratic term, and then I do the tilt, I will get a linear term. And then typically, so I really have to make sure that I'm actually sitting at the point where these two interfaces are sitting on top of each other. Yeah.
Thank you.
You have at one time derived this Fibonacci sequence of fixed points. So what is the relation to this scenario? Because that's also coupled KPZ equations. You know, you have n components and then you get critical exponent which is not 3/2 but ratio of...
For n components, I have no, I mean, the only thing which we know for n components is you know, this analog of the cyclicity, but otherwise, you know, the n component is totally, I mean, untouched, right? It's only the two-component case which we can...
Okay.
Yeah.
So, if I understand well, also numerically, you see that on the Kohl-Hopf line, fluctuation dissipation is restored, right?
Correct, yes, correct.
But if you move outside, you don't, it seems stuck. You don't see flowing to the fluctuation dissipation.
No, I mean, let's see. So what I'm saying is that, of course, I mean, it's somewhat modest evidence, but, you know, I mean, this is sort of, I guess, what you call the fluctuation dissipation line, right? It's a diagonal, right? And so what I'm saying is that, you know, wherever you start, I mean, let's say at this point, and then, you know, if I do the scaling limit, I will be on the fluctuation dissipation line.
But do you see
it's a very simple flow diagram, right?
But do you see numerically?
Well, as I said, I mean, numerically, I think, you know, of course, you know, the most compelling evidence is sort of along this Kohl-Hopf line, right? I mean, there we have, we have essentially a sort of semi-vigorous argument, at least sort of, a very clear argument why it should be the case. And we have sort of two rather different sort of numerical simulations, confirmations, because you see here, what he studied is actually, he starts from the flat interface, and then he observes the GOE Tracy Witham distribution, whereas here we do the stationary case and we see the FKPC. So this I would think is really secured. For this case, I think, if you believe in this picture, I mean, the data are convincing, but as I said, I mean, we're running more simulations to make it even more thing. And it's just a simple thing. I mean, you of course, you have to sort of, do numerics in order to get, the scaling form of the dynamic correlator, and then when you want to fit to the data which you have from this point, which are sort of relatively rather precise, I would say, up to a scale, they just have to be on top of each other, right? I mean, that would be sort of the confirmation. And it looks like this, but I mean, it's maybe slightly, yeah.
Okay, so maybe we thank Herbert.
Thank
for
you.
this.